Hello students. So in the previous video lecture, we have seen expectation maximization algorithm, how it is used to solve the problem of likelihood estimation as well as the problem of latent or hidden variables or unobserved data. So now in this particular video session, we shall see a few numericals that can be solved using maximization, expectation maximization algorithm. So numericals on EM algorithm. Expectation maximization algorithm, where we know the maximum likelihood estimation estimates the unknown parameters of a probability distribution given a set of observations. So, maximum likelihood estimation can estimate the unknown parameters when the set of observations are known. Although MLE is a very useful technique, it assumes that all information about the observation is available. Let's take an example. We consider two coins and we want to toss these coins A and B, which have probability of it being head as P and probability of it being Q as tail being Q respectively. Each time one of the coin is chosen at random and tossed, the following sequence is obtained. So this is the sequence that we get when we consider two coins and we toss, and this is the head and tail probabilities. So the values, we have to estimate the values of P and Q. Okay, so probability of it being head or tail from the given data. So expectation maximization algorithm here in this case is very easy because we'll directly apply maximum likelihood estimation for this problem. So if you see over here, we can find out P, that is probability of the occurrence of head for coin A is nothing but the number of heads with coin A divided by the total number of tosses with coin A. So we will check for the number of heads 1, 2, 3, 4 and 5. So number of heads with coin A, total number of tosses with coin A is 9. So we will be getting the probability of a coin tossed it being head as 5 by 9. In a similar manner, we will be doing it for coin B. So the number of heads for coin B is 4 and the total number of tosses with coin B is 7. Let's take another example. Assume that we have got two coins C1 and C2. Assume the bias of C1 is called theta1, which is nothing but acting like P, the probability of getting heads with C1. Assume the bias of C2 is theta2, that is probability of getting heads with coin 2. We want to find theta1 and theta2 just as we saw in the previous slides how to find P and Q by performing a number of trials. So the first experiment is we choose 5 times one of the coins. So one of the coins is taken C1 and C2 and we choose 5 times and we toss the chosen coin 10 times. For example, if I am choosing coin C2 or B. So if that coin is chosen, I am going to toss that particular coin 10 times. So we can see the observations over here. So theta1 will once again be the number of heads using C1 divided by the total number of flips using C1. And theta 2 will be the number of heads using C2 divided by the total number of flips using C2. So here is your table where if you consider coin A, you are getting 9 heads and 1 tail. And again, if I am considering my third instance to be coin A, 8 heads, 2 tails. And my last instance, if it is coin A, it is 7 heads and 3 tails. Similarly, for coin B, I am getting 5 heads, 5 tails and 4 heads, 6 tails. I will simply perform summation. So for coin A, I am getting 24 heads and 6 tails. And for coin B, I am getting 9 heads and 11 tails. So theta 1 will nothing be 24 upon 24 plus 6. So my probability is going to be 0.8. That is, there are 80% chances. Alright, of theta 1. And whereas in this case, the chances of it being coin B is going to be 0.45 probability, that is 45% chances. So this is how maximum likelihood estimation works, because we know which coin it is, whether it is A or B or C1 or C2. So well, that was easy because all the information required to compute the unknown parameters, that is theta 1, theta 2 or P1, P2 was available. But what if the labels on the coins were hidden and you did not know which coin was used for which toss? Basically, if this part was hidden, then what would you do? Given that the coins are equally likely to be chosen, how will you estimate the unknown parameters P and Q or C1 and C2 or theta 1 and theta 2? How will you find this if the labels are not given? So this is a more challenging problem. See over here, we have considered the similar 5 experiments, but we do not know the identities of the coins used for each of the tosses. So we are going to treat whatever values which are not shown, they are hidden variables or latent variables. Okay? There was a question asked in your university examination. Explain how initial hypothesis converges to optimal solution. Explain with an example. You can consider this particular example for your reference. So moving ahead. So if you observe over here, these are nothing but the 5 experiments. Okay? And on each of these 5 experiments, we will be applying the expectation maximization algorithm. So if you see over here, if the first point of the algorithm says we are supposed to assume some observed data which is coming from a specific model. So if you see number 1 over here, we are assuming theta A and theta B to be 0.6 and 0.5. And now we are going to give that to our expectation step. So let us see how our expectation step works. So we have assumed this is our initial guess for the unknown parameters. So in the first round, if you see, we have got 5 heads and 5 tails. So 1, 2, 3, 4, 5 heads and 5 tails. So we calculate the likelihood using binomial distribution. So the formula is nothing but P of K is equal to theta of K. K represents over here the number of heads into 1 minus theta. Theta is nothing but the initial guess values that have been considered in raised to n minus k. N is the number of tosses In our case, n value is 10 because we have done n tosses. So when I'm finding out the likelihood of A and B, the value is nothing but, theta is nothing but 0.6 raised to the power head. Head value is nothing but 5 in our case for the first experiment, into 1 minus theta, which is 0.6 for A, raised to 10 minus 5, because 10 is the number of tosses done. For B, everything remains the same. The only change is the value of theta. Instead of 0.6, we take 0.5. Both the values are calculated. For likelihood of A, we get 0.00079. And for likelihood of B, we get 0.00097. Now we need to normalize these values. So simply what do we do? For A, we do it 0.00079 divided by the sum of both these. So we get 0.45. And for B, we will perform the same operation, or simply you can do 1 minus 0.45, which gives you 0.55. Now, we will estimate likely number of heads and tails for the first toss. So we have got 0.45 for A as the head and 0.45 as the tail for coin A. And these are nothing but the number of heads and the number of tails for the first toss, 5 and 5. And for B, we got 0.55 as calculated in the previous slides. And similarly for tail. So we get the values as 2.2, 2.2 head and 2.2 tail, as you can see over here. Similarly for B, it is 2.8 head and 2.8 tail. Now this we have done for the first toss. In a similar manner, we will have to do it for the remaining 4 tosses, second, third, fourth and fifth. So theta remains the same, 0.6 and 0.5 for A and B respectively. Our second toss, if you see, I've taken a part over here. So what will happen in this case is, this is an error. The number of heads over here should be 9 and the number of tails over here should be 1. Please rectify this. It is 9 and 1. The same formula implies you get likelihood of A to be 4.03 into 10 raised to minus 3 and likelihood of B you get 9.76 into 10 raised to minus 4. When you normalize this, you get for A value as 0.80499 and 1 minus 0.80499 will give you 0.19500. Now what we will be doing next is estimate the likely number of heads and tails for the second toss. So we are going to perform the same procedure. Whatever values we got in the previous slide, we are going to use those and multiply with the total number of heads. Here in this case it was 9 for the second case and tails it was 1. So you can see 7.24 heads, 0.8 tails, 1.755 which is approximately 1.8 heads and 0.19 which is approximately 0.2 tails. In a similar manner, we will be doing for the remaining 3 tosses. And once we obtain these values, we will perform the summation. So while performing the summation, we get 21.3 heads, 8.6 tails, 11.7 heads, 8.4 tails. Now the output of this will be used to calculate the value of theta A and theta B. This is nothing but your M step, maximization step. So it is 21 upon 21.3 plus 8.6, which is approximately 0.71. And theta B value is 11.7 divided by 11.7 plus 8.4, which is 0.58. Now, this value will be now given as an input over here. So our initial guess, which was 0.6 and 0.5, will be replaced with 0.71 and 0.58, and the same operation of expectation will be performed. It is an iterative procedure, and this entire procedure takes place until the value of the previous iteration and the current iteration of theta is approximately the same. So if you see over here, this was your first iteration. So when you perform the 10th iteration, you get approximately the value of theta A and theta B as 0.8 and 0.5, which means in the 9th iteration you might have got a similar value, and in the 10th iteration you are getting the similar value, that is 0.8 and 0.5. So because we perform this until your step 2 and step 3 are converged. So this is an example of expectation maximization algorithm or EM algorithm. Thank you.